Where are we going here? Let's start here. We're going to be talking about random sampling. We're going to learn some new Excel functions. But this, I brought this up on Tuesday and I'm bringing it up again today. This is our Z equation from now on. And I want to make sure you see the difference right there, that little part right there. The square root of the sample size is part of the denominator. It's being divided into the standard deviation. You do that denominator, you do the numerator, and then you divide that last step. Denominator into the numerator. So you've got to do this part right here. This denominator is no longer called just standard deviation now, it's called the standard error, which changes the Excel equation, because now that third number is no longer the standard deviation, but the standard error. It's always been the standard error, but we've always only had one in our sample size, so we just called it the standard deviation because the standard deviation divided by 1 is the standard deviation. But I want to make sure you realize now that third number is the standard error. It's divided by the sample size, which on Tuesday, I'm going to go over several examples where we have some sample sizes involved to help prepare for the homework. Today, I'm just going to give you some, this is actually the big hint, in case anybody wants to start the homework early, is this right here, and what I just said right there, because, let's take a look at that homework. I haven't even gone over the old homework yet. Hang on, way ahead of myself. But hang on, here's the new homework. It says, like 1A, for example, a random sample size of 49. There it is right there, right off the bat. So I'm basically telling you now, this is the new formula you're using on these new equations. Random sample size of 49, taken from a population with a mean equal to 50, standard deviation is 6.2. We have this big population, 50, 6.2 is the standard deviation, but we're grabbing 49 out. Not just, what's the probability that one of them, or A, however it's worded, now it's 49. Show the detailed work manually calculating the Z-score, then give the norm S distribution. Have we learned the norm S distribution? I think I forgot to add that today. Again, audible, calling it audible. Hang on, here we go. Norm S distribution. This isn't norm distribution. This isn't this. This is used when you manually calculate Z, and now we no longer look at a Z chart. We just enter the Z into the parentheses, equals norm S distribution, put the Z in the parentheses, it looks up the chart for you. You know, no longer, now we're not going to use the Z chart. I don't think we're even using it on final exam. And every problem on this homework for this week, that's due a week from today, you're using norm S distribution along with the manual equation. You're replacing the Z lookup. Now, you're not replacing the Z equation. That would be this Excel function right here, norm dot distribution. That's replacing the manual equation. You're only replacing the Z chart after you use the manual equation with that. So anyway, it says, show your detailed work manually calculating the Z-score, then give the norm S distribution equation and the result. Define the probability that a sample mean would be less than 52. So it's asking about 52 or less. The mean is 50. The standard deviation is 6.2. And the additional information, the sample size is 49. But once you calculate Z, don't then look at a Z chart. Use your norm S distribution. There's 1A. Then you go to 1B. It says, write the Excel equation and result to solve the above question. I'm asking for this. Norm dot distribution on B. All of these, and I think there's 6 of them, have A and B. They're worded almost the exact same way. Every single A, you're solving manually, but using norm S instead of a Z chart. And every one of the B's, you're using this equation one way or another, maybe with a 1 minus in front, maybe blah, 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 or something like that. So there's all the A's, there's all the B's. Does everybody understand, in case you want to start the homework early, does everybody understand what's expected on these problems? 1, 2, 3, 4, 5, 6. 6 of them. 6 A's and 6 B's. Everybody get it? Will you start early? If you want to wait till Tuesday, I'm going to go over several examples that are exactly like these problems that will probably help you. But if you want to start early, you now have enough information. All right, I want to talk about this. Wait, this is where the video starts. Okay, let's go to the new stuff. Now I'm getting the hat. You ready? I may have already mentioned this a little bit before, but I really need to emphasize it because some of you are gonna be managers. And believe it or not, for big companies that sometimes you gotta use a statistical process when it comes to things. And this is a perfect example of where a manager says, hey, I'm gonna use a statistical process because I wanna be able to report some numbers to a meeting that I don't have the real numbers for it at this point in time. So this is an admissions director, I think. Let me see here, is that kind of receipt? Admissions director, they got 900 applications for the fall. So here's the 900 applications, or they have accepted 900, whatever the case may be, there's 900 applications involved. And this manager of the admissions department has to go to a meeting and report, hey, what's the average SAT score of this incoming freshman class? And what percent of them want to live in housing? Well, there's no way, sometimes you get requests that there's no way you have time to take all 900 of these and figure out what that would be, what the average SAT score is. So it's very appropriate to say, you know what I'm gonna do? I'm gonna pick out 30 of them. Now here's the key in real statistical research. If you're a manager and you're really gonna do this, you have to have at least 30. That's kind of a golden rule. 30 should be your minimum sample size if you're really gonna use this to go to a meeting with some numbers that you got from using statistical inference, it's called. What you're gonna apply from this random sample to about the whole population, called inference. You're inferring. So as long as you use at least 30, but the key to this working and going to that meeting with a number that could be close to the reality of what the number really is the random process of that 30. The process you use, and there's a million different processes. But you gotta keep asking yourself, whatever process you decide to use to say, I'm gonna pick 30 out of that 900, the rule is that every one of the 900 has to have the same equal chance of being one of the 30. Everybody hear that? That's what randomness is all about. Random sampling is all about that every item has the same equal chance with no bias of possibly being one of the 30 that were chosen. And that's how it works. That's how this whole statistical inference works, that you can make this kind of revelation about all 900 on only 30 of them because every one of them had the chance to be one of those 30. And the odds of those 30 being so far different than what all 900 would be are very slim as long as every one of them had the chance to be that 30. And you use a true random process. Now, here's old school. You ready? Hang on, where's it at? Here it is. This is when I was in college. This is how we had to do it. This is real. Matter of fact, in business even. But when I finally graduated from college and got to business, Lotus 123 spreadsheets got invented. And they had a way for you to use random process. Then came Excel spreadsheets, which by the way, should have been sued by Lotus 123, just so you guys know, because they literally ripped them off. It's almost the exact same spreadsheet. This is called a random table of numbers. This was used by everybody in statistics that are truly gonna use random sampling. And it was the way, when you take a stats class, not only did you get your regular book, but you got this little thin paperback book that had maybe 30 front and back pages of nothing but looking like this. Just random numbers like this. And when we're in a class, so everybody was using the same numbers, the professor would go, okay, everybody, for this assignment, we're gonna use page, whatever page this is, page 200 or 22. And I want you to use column 5. So everybody has to use column 5. And how many applications were there for the incoming freshmen? Tell me again, how many? Was there 900? How many digits are there on 900? 3. So then you'd be told, use the far right-hand 3 digits. You have to use the same amount of digits as the largest number that could possibly have been selected in the population. So now, whether it be hypothetical because of the way they're stacked, or whether you officially do it, you somehow have a number 1 through 900 representing these applications. You don't have time to pull out all 900 and figure out everybody's SAT score and find the mean. So you go, okay, I'm going to row 5, column 5, because you just randomly picked it, or were assigned it. Let someone else even tell you what column to use. And I'm going to use the far right-hand digits, 3 digits, and with those 3 digits, they're going to tell me which 30 to pick out of there. And I keep using these digits until I've gotten to 30, because these digits sometimes will give you a number that's over 900. We can't use that. 932, there is no 932. You keep going down the list until you finally got 30 out of the pile. So help me out, what's the first number? I don't even know the first number right now. We have to remember what was just assigned to us. This is the page, what column? 5, hang on, from the left. 1, 2, 3, 4, 5, I see it. Which digits are we using? 705, the far right 3 digits. I'm going right now. 705, pulled out. There's one of our 30. What's the next one I'm pulling out? 48, 048. I'm pulling out number 48. Some of you probably thought we'll never get to the small numbers. There's a perfect example where we did, and that was pure luck because I have, there's no way I have any of these numbers memorized whatsoever. What's the next one? 569, that's within the, how many, 600 or 900? 900. Yeah, that's in there. That's in the middle of the pack. Boom, pulled it out. What's next? 358. Let's keep going. 703. Do we have a 703? I keep thinking there's only 600 there.
How is this random? Is it each, if you're going straight down a line? Yeah, but if you're going straight down a line.
Those numbers have no meaning. They were just printed on there with no sense whatsoever. These are nothing but random numbers. And we could have said, let's use the middle 3, or we could have said, let's use the left 3, or we could have said, use column 10, or we could have said, use another page. It was that, this is exactly how it was done. Every single number you can think of is represented in these random numbers somehow or another, in nothing but randomness. Yeah, and it could have been, the only reason we're all going to use the same numbers because we've all been assigned, we're all in the same class, and we were assigned column 5, far 3 right digits. The far right 3 digits, right? And that's how it was done. Okay, life is easier now. Now that you've experienced my life, life is easier. We have Excel now. And we have ran between, and we have, where's the other one? Ran. Let me make sure you get this. Let me click on one. There it is right there. Equals RANDBETWEEN, parenthesis, the lowest number in the range, comma, the largest number in the range. And we have 900 applications here that we numbered 1 through 900. Now, I want to make sure you understand, this is only used with discrete data. Because we have these applications numbered 1, 2, 3, 4, we can use ran between. But if we weren't using discrete data, we were using continuous data, somehow we're using like 1.12, 1.15, 2.17, something like that, then we would use RAND, parenthesis, with no space between them. I want to make sure I know this is hard to believe. First time I saw this, I said it didn't even make sense. Equals RAND, left parenthesis, right parenthesis, no spaces. Nothing between the two parentheses. You're telling Excel to randomly pick a number between 0 and 1. That's what that statement does. Now let's go back to the top one though, because I want to stick with this, this college admissions office here. So right now, what happens with Excel is if you change any cell on this spreadsheet, anywhere that RAND, whether it be the RAND between or the RAND parenthesis, a new number gets selected. When I opened this spreadsheet, those are all new numbers that weren't there when I closed it last. When I put a space in the cell I'm in right now and hit enter, those are going to be new numbers. The top one is going to be a new number between 1 and 900, and it could be 11 again, it's possible. And the bottom one there is going to be some number between 100 and 200, and it could be 195 again. The odds of that being 195 and the top one being 11 both again are so slim that I'd put everything in my pocket on it that no way it could happen. But here we go. You ready? I don't know how much I have in my pocket, but trust me, it's not much. Space, enter. Now we're at 579 on the top one, 110 on the bottom one. We're just talking about the top one. I now just reached in and got number 599, space, enter. Now I got 232, space, enter. Now I got 538. So you can see now today, there's a much easier way to come up with random numbers between a certain number and a certain number with discrete data. And we can pull out all 30 of them.
I'm sorry, you just click space enter from
There it is. Yep. Again, I'm go up. Look at it, I'm going up now. And it keeps changing. I want to show you something. On this spreadsheet you see right here, I showed you this last week, this simulation. All these different things are being simulated, market size, market share, all this. I want you to notice, hang on a minute, hang on, watch. This cell is using RAND parenthesis. This cell is using RAND. Look at how many cells are using randomness. Here, this one's using RAND between, RAND. Now, I'm gonna put a space in this cell right here, F9. I want you guys to stare at the numbers down below here though, and watch them all change when I put a space. Every time anything changes on this spreadsheet, every one of those random numbers change. Here we go. Everybody see it? Every time you open it up, and that's the whole thing about a simulation, is that it's constantly simulating all the different things that could happen out there in the real world, based on the information you fed it though. A simulation is only as good as the humans who made it. Like through meeting after meeting, look at the different things we did come up with. We came up with, we're going to be investing somewhere between 7 million and 10,500,000. We know that. This project could run with extra expenses, so we could get up there closer to 10 million. If everything goes perfect, we could spend as little as 7 million. And then after the run, by the way, this whole process with this machinery is only going to be somewhere between 6 and 15 years. We know for sure this will make it through 6 years. It could go as long as 15 years. I mean, there's all of these things that are out of your control that could really happen in a business plan, in a business venture that you're thinking about going in. And that's what this simulation does. It takes all the possibilities into it. Residual value. Now look, if after we're done with this project, if for some reason we only wanted to go 6 years, we can still sell the equipment for $5 million. We get $5 million back maybe. Or maybe we sell the equipment even on the low side because we got it to stretch out all 15 years. We're still gonna get $3,500,000 back approximately. By the way, those are very high residual values compared to real life. Usually in my experience, the total investment, especially on machines, that you get after somewhere between 6 and 15 years is more like nowhere close to 50% of its original value. Nowhere close, more like 20% of its original value if you're lucky, depending on how long the machine was. But the thing is, you can get residual value. And all you accounting majors, you understand the depreciation of it, and you depreciate it, and sometimes you'll depreciate it in full, but if you get a residual value, you now have residual income you have to report back because you took the depreciation all the way to zero on that piece of machinery. That's why a lot of accountants will not take it to zero, knowing there's gonna be a residual value, and not have to then pay the tax on that residual value. Even though you got the tax break along the way, doesn't mean you have the cash set aside for all of a sudden you sold it for $5 million, you gotta pay the taxes on that because you took the tax break for the last 5 years before that. Anyway, that's accounting for you. Great. That's my point. So you learned how to use RAND between. Now, that's it again with discrete data. It's very easy. You put the lower number in the parentheses and the upper number. Now, here's the more difficult one. RAND parentheses. Here's a real common way it's used, and this is exactly how it's being used on the simulation. Look at this sentence right here where I'm pointing. It says, here's an example of randomly selected number between $45.10 and $62.30. I always use the example of, let's say we're thinking about expanding this business, or that simulation was about expanding the business, we're gonna make golf bags. I always use golf bags as an example. We're a golf company, we make golf clubs, we make golf balls, but we haven't been making golf bags and we want to expand into golf bags. We know that the material for these golf bags is gonna be, hypothetically, somewhere between $45.10 and $62.30. Because there's pennies involved, this is what makes it continuous data. This isn't saying, hey, it's gonna be somewhere between $45 and $62, $46, $47, $48. Then we could use RAND between, but this has all these pennies involved. So we're gonna use RAND parentheses. We wanna simulate every possible material cost. Let's say we have a year where material cost is as good as it can get, and it only costs us $45.10 for every one of the golf bags we made. That's great. But a simulation will also simulate every golf bag we make, material costs $62.30. So we can see what the worst scenario is in case our suppliers, end up jacking up the price halfway through the year and we didn't see it coming. It simulates every possibility, but at the meeting, we all agreed material is gonna be somewhere between $45.10 and $62.30. Now, here's how you simulate it. You start with the lowest part of the range of the price, or whatever the range is, the lowest number of it, equals, and you could do this with the largest number and subtract, but I usually use the lowest number. And then I add, put plus, RAND, parentheses, parentheses, meaning pick any number between 0 and 1. For example, let's say it just came up with 0.50. 0.50 Excel just came up with. You multiply it times the range of the full range that you think that this cost could be. Material is going to be somewhere between 45.10 and 62.30. What's that range? 45, 55, what is that? 10, 15, 60, $17.20. Here it is, $17.20. So what's happening is, every time I change a cell, that number is going to change to some number between these two, based on that. If that comes out to 0.50, it'll be half of that $17.20 added to 45. It'll be right in the middle between them. If that comes out to 0.20, it'll be really close to 45.10. If that comes out to 0.90, that will show up to be really close to 62.30. See how it works? It allows you to randomly simulate every possible cost of labor, of materials, Okay, now here it goes. 47.64. Now we simulate 47.06. Now that's just purely a coincidence to be 47 twice in a row. Here we go. 56.82. $50.07. 59.96. Excuse me. We haven't got one in the 60s yet, but that's only like that's less than $2 away, or just a little over $2. 45.17, hang on. 48.69, 45.46, 56.10, 52.09, 55, or 45.30, 48, 53 is, anyway, you guys get the picture. Every time anything changes on the spreadsheet, and that simulation I just opened up, if I were to just change any cell, everywhere there's RAND in some fashion, every one of those numbers change. And so you're just constantly simulating. What's the advantage of using this randomness in a simulation? Let me show you the advantage. Are you ready? Hang on. It's these numbers right here on this table. If you got a simulation, you get it working. This is a final meeting where we all look at each other and we go, okay, what's the simulation telling us? Should we make golf bags or not? And I always run to that probability of a loss. Does everybody see on the right-hand side? What percent chance of us losing money is there? 44% chance. We're putting up, how much? How many million? I can't remember, was it 4 or 5? 5 to 10 or 7 to 10.5 million, right? No, I had more. It wasn't 7, was it? 7 to 10.5 million? Oh, there it is. Thank you. There's no way we're going to take a 44% chance of doing this and coming out with a loss. And that's so high that the meeting would be done. That's it. We're not going forward. Let's think of something else, what we want to do to make this company grow. But let's say that 44% we're closer to, let's say, 15% or 18%. Now debate takes place. And we start saying, here's what could happen, here's what could happen, what's the worst scenario? Okay, let's say it's 15% loss and we do get a loss. What's the worst loss we could have? That's always asked. What's the worst? How much cash could this eat up? Where's the answer? Max loss. How much cash could we eat up? 18,640,000. Everybody see it? Should I point it right there? $18,642,165. That's all. Just 18 million. That's all. That's all the decision's about. The possibility. That's what simulation does. It allows you to see reality. And especially when there's that many millions of dollars involved. So that's why you guys got to learn these simulations. I hope that you get more into the simulation in operations or the information systems, whatever it is, management class, or there was one other class it could have been, management science. I don't know if that's a required class or an elective, but that's a class I used to teach. That was kind of my expertise, was that management science class. And I always made sure everybody knew how to do simulation. We spent a whole week on it, and everybody had to hand in a simulation project. So that's how important it is in the business world for big companies. Small companies aren't sophisticated enough to spend the time to put this together and do all that. They've never even, when I worked for this consulting firm, I went and traveled from company to company each week, helping them figure out why are they not making the kind of profit they should be making. I'd spend the first day going through their financials, figuring out, and what I'm looking for over the last few years is I'm figuring out which expenses are out of hand. What took place, and it allows me to pinpoint the category the expense in by looking at the financials. Something got out of place, and it's as a percent of revenue. It's not making sense. Why is this so high compared to where it was 5 years ago? That allows me to key in then on what is going on in that area that's causing them to not have the kind of profit they should be having. And this is sometimes some of the things we introduce to medium-sized companies that have not gotten into this because they went ahead and went forward with projects not knowing how much money they could have lost and end up losing money. Not necessarily the amount they could have lost, but to do all that work and all that manpower just to lose money is not worth it. And the simulation would have told them that in the first place. That's how much important simulations are. So anyway, you now learn how to use randomness and how to write random equations. And RAND is throughout the simulation all over the place. One last thing, I think you already know, but I just want to make sure you know, SQRT, because now that we have to use the square root of sample size, right here on the standard error, it's going to be like, you're going to put standard deviation, whatever that number is, divided by SQRT, parenthesis, whatever that sample size is, right there. That's how you got to write it for the Excel equation, SQRT, instead of, there's no square root symbol, but instead of calculating that, just put the whole standard error right there in as the third number in the parentheses for normal DIST, normal distribution. Okay, so here we go. Blah, blah, blah. Wait. Where did we pick the numbers out? Where are they? Here we have 3 digits. There's 3-digit numbers because one's 900. We start picking the numbers. 744, we got 744, 436. They got a 90. This is showing you what would happen if you had to use numbers to pick out the 30. Here they are. Here's the names. Here's the SAT scores. Here's all 30 of them. Here's whether they live on campus or not, yes or no. Because that was the 2 things that were asked about for us to go to this meeting with. Of the 900 students coming in freshman class, what's the average SAT score? What percent are going to live and want to live on campus so we can have student housing prepared? So we did all that, and we go to this meeting, and we come up and we say, the average SAT score based on a random sample of 30, because we haven't got these applications into our system yet, was 997. Everybody's going, oh yeah, okay. And then housings were just waiting for this number. What percent in your random sample of 30 said, yes, I want to live on campus? Right here, 68%. So the housing director says, okay, I'm going to go ahead and plan then on 68% of 900 most likely moving into our dorms, and I'm going to plan ahead. I'm going to start hiring RAs, get training, make sure all the bedding's washed, Here's how close we were to reality. We went into that meeting, said 997, it was really 990. We said 68%, it was 72%, but we're able to tell housing, hey, you're planning on 68%, it's going to be more like 72%, but that's such a small difference. Our sample really did give them a good idea of what the incoming freshmen to expect without us we didn't have the stuff in there, and that's how you use this in real life. Go ahead, Amit.
So is it possible to take the SAT scores without doing it manually?
The 30 of them?
Yes.
Well, yeah, you could throw them in the air and catch 30. I don't know if the 30 SAT scores were already entered into a database, yes. But they weren't. They're just sitting there piled up still. Nothing was entered in the computer yet. We're, like it's July or something type thing. Yeah, you're right. Yeah, you could have just do an array, say now pick 30. All right, so now just a few things. These are going to help you for the true and falses, or there's no true and falses. The multiple choice for the final, there's a few definitions from this chapter since this is a new PowerPoint for us. So I'm going all the way back to slide 2. Write these subjects down so you know to study them. One is going to be statistical inference, and I talked about it already in the lecture. Whoa, hey, come on. What do you mean you can't see it? Hang on. All right. One is called statistical inference. Again, it's all about if you use true randomness and every item in the population had a chance to be part of the sample, you can make some inferences about the population. It will give you good hints as to what the true numbers are of the population. So there's what's important about that one. Slide 3, proper sampling method, I think is what I wanted to point out here. I'm trying to look at my notes here. With proper sampling methods, the sample results can provide good estimates of the population characteristics. It allows you to infer things about the population if you do the sampling correctly. Some of you are going on to your master's, and that's about using samples and applying statistics to the sample. So you got to realize how to do this. No, I'm going to slide, what is this, 4? No, we're going to 6. 6, I want to point out finite. I want to make sure you understand the difference between infinite population and finite. Everything we talked about, the random sampling process, had to do with finite populations, meaning there's a certain number in the population. Those applications we talked about, there were 900 of them. We don't have more applications being added to it every minute that goes by. That would be infinite, that the population keeps growing and changing in size. We've been talking about finite populations where the size is in stone now. We're only accepting these 900 applications. So we only had to number them 1 through 900. It's not growing at all. And that's the kind of sampling we're doing. If you do get, let me see, where's infinite? When we get to slide 9, I'll talk about infinite in a minute. Okay, now slide, what is this, 7. We're talking about, sampling. The most common sampling you're gonna run across is especially being down in southeast Michigan, is a manufacturing process. All of them are using statistical process control, quality control. And so, with quality control, when you get to the end of a run, meaning you manufactured something, before your client that you're sending it to will accept that order, they send someone over to your business to sample it. And let's say you're making ball bearings. They're pulling out 30 ball bearings, and they're measuring them with their machines, and then they okay, and now you know you're gonna get paid, and you ship the 20,000 ball bearings to your client. That's how it works in the business world of manufacturing. So the deal is, there's different ways of sampling. There's what's called sampling with replacement and sampling without replacement. In my experience, I've always seen sampling without replacement when it comes to statistical quality control. They pull out the 30, they measure them, they set them aside, they pull out 30 more. They don't put those back because there's so many thousands of them in there, they don't need to. So they pull out 30 more, measure them, and they'll do that maybe 3 or 4 times, maybe even 5 times, depending on how important the measurements are. And then they put them all back after they're done. But that's called sampling without replacement, and that's the most common sampling that takes place. So I want to point that out, especially if you want to remember which one's the most common. And then on this slide, I wanted to point out, situations where we can't use the sampling method that I taught you today is when we have infinite populations. The population is so huge, no way could we number them all to get a random number to say, okay, you're part of the sample. Number 1,295,000, we could never get it all numbered. So that would be an example, and right here, by the way, is infinite population descriptions. It's where, like an ongoing process where the population size keeps getting larger and larger because you keep making more and more of them, let's say in a manufacturing process, for example. In that case, then, the sampling is a little different in that you do it where you try to give every item in the population a fair chance, but the fact that the population keeps growing, you don't necessarily are really giving every one of them a fair chance. So the rule is that you have to choose the sample size, each one of them independently of each other. You can't reach in and grab 5. You gotta grab one at a time, maybe shake them up, grab another one at a time. So if you have an infinite population, however you're doing your sampling, every one of them have to be done independently of each other. You can't grab a bucket load of them or something like that. Okay, that is all I've got for today, you guys. Don't forget, Tuesday we go over the stuff necessary for the homework. Have a great weekend. Cool. Hey, my